Humanity will live in space, but the real question is, when? For years, scientists and aerospace giants have been telling us that one day, humanity will leave Earth behind and settle on a different planet. In short, they see the future of our species out there among the stars. So, when and how will this actually happen? When will we reach the technological level required for such a leap? And even if we do, is human psychology resilient enough to handle a migration of this scale? In today's video, we're going to try to answer these very questions. But before we jump in, don't forget to subscribe to the channel, like the video, and drop a comment with your ideas for future topics. First, let's get one thing straight. To understand humanity's future in space, we can't just rely on our imagination, theories, or love for science fiction movies. If we truly want to grasp what lies ahead, we need to look at ongoing scientific research, active engineering projects, and published academic studies. Living in space is no longer just a sci-fi trope. It's a reality that is closer than ever. The fact that agencies like NASA, ESA, SpaceX, CNSA, and Roscosmos are actively working on this and pouring massive portions of their budgets into it proves that this dream is backed by concrete steps and tangible goals. This journey is generally analyzed in three main stages. First, establishing a permanent presence in low Earth orbit. Second, colonizing our solar system. And third, expanding into interstellar space over the long term. To elaborate on the first stage, work done aboard the International Space Station has given us deep insights into how the human body reacts to microgravity. Long-term biomedical research, such as NASA's TWINS study, revealed the effects of prolonged spaceflight on gene expression, the immune system, and cellular aging. Researchers observed temporary increases in telomere length while the astronaut was in space, though these values quickly returned to normal upon returning to Earth. At the same time, as I mentioned, astronauts experience muscle atrophy and lose about 1 to 2% of their bone mineral density per year. While that percentage might sound small, it poses a severe risk for long-term missions to Mars. Scientists have conducted numerous experiments to solve this problem, and one of the most promising concepts being developed is artificial gravity. The plan is to use rotating habitats to generate a gravity-like effect via centrifugal force. This idea traces back to Gerard K. O'Neill's cylindrical space colony designs from the 1970s. Today, this concept is being re-evaluated through models like the Stanford Torus and the O'Neill cylinder. Designed as massive rotating habitats several kilometers in diameter, these structures would house agricultural, residential, and industrial zones inside. Another critical hurdle for life in space is radiation. On Earth, the average annual radiation exposure is around 2.4 millisieverts. On the ISS, that number jumps to anywhere between 80 and 160 millisieverts. As you can see, even in relatively close orbit, there's a massive difference. On the surface of Mars, the measured average is around 230 millisieverts per year. Sustained exposure at these levels dramatically increases health risks, particularly the risk of cancer. Because of this, scientists are researching radiation shielding using water, polyethylene, and regolith, planetary soil. In fact, current plans suggest building Mars colonies underground or covering them with thick layers of soil. The second stage, colonizing the solar system, is directly tied to missions currently in motion. NASA's Artemis program aims to land humans back on the moon and establish a permanent base there. While the Artemis 3 mission targets a crewed lunar landing, concepts like the Artemis Base Camp are being developed to create a sustainable habitat. Regions near the lunar south pole, such as Shackleton Crater, are especially critical because their permanently shadowed areas contain water ice. Water on the moon isn't just essential for life support, it can also be used to produce rocket fuel. By splitting water into hydrogen and oxygen through electrolysis, we can create liquid propellant. This technology, known as in situ resource utilization, ISRU, has the potential to drastically cut mission costs. Producing fuel in space rather than dragging it from Earth heavily reduces the logistical weight of deep space endeavors. Mars colonization, however, presents a far more complex engineering problem. Mars has an atmospheric pressure of roughly 0.6% of Earth's, and its atmosphere consists mostly of carbon dioxide. However, the MOXIE instrument aboard NASA's Perseverance rover successfully extracted oxygen directly from the Martian atmosphere. This experiment offered major proof that sustainable life on Mars could actually be possible. Growing food on Mars will require controlled environment agriculture (CEA) systems, where light, temperature, humidity, and gas levels are entirely artificially regulated. Furthermore, Martian soil contains high concentrations of toxic perchlorates, making direct farming impossible. This means we'll need soil decontamination technologies or completely soil-free farming methods, such as hydroponics and aeroponics. When it comes to power generation, the plan for Mars involves a combination of solar energy and nuclear reactors. NASA's Kylo Power project aims to provide continuous energy to space colonies using small-scale nuclear reactors. These systems are especially vital during global dust storms that can render solar panels completely useless. Mining asteroids, one of the most promising pillars of the future space economy, is grounded in serious scientific research. Metallic asteroids like 16 Psyche are believed to be immensely rich in iron, nickel, and platinum group metals. NASA's Psyche mission aims to analyze this asteroid to give us a clearer picture of its composition. If these resources ever become economically viable to harvest, it could fundamentally disrupt global metal markets on Earth. Meanwhile, space tourism is a sector that has already kicked off. Companies like Blue Origin and Virgin Galactic have successfully launched suborbital flights, while SpaceX's Crew Dragon capsule has carried private citizens into Earth's orbit. These milestones are a clear indicator that space is opening up for commercial enterprise. To understand interstellar space, we first have to grasp the sheer magnitude of the distances involved. The average distance between Earth and the Sun is about 150 million kilometers, defined as 1 astronomical unit, AU. However, the nearest star system, Proxima Centauri, is about 4.24 light-years away. 1 light-year is the distance light travels in a single year, roughly 9.46 trillion kilometers. That means even our absolute closest neighbor is nearly 40 trillion kilometers away. Voyager 1, one of the fastest spacecraft ever built, travels at around 17 kilometers per second. At that speed, it would take Voyager roughly 70,000 years to reach Proxima Centauri. This reality makes it crystal clear that our current technology is completely inadequate for interstellar travel. Because of this, scientists are shifting their focus toward propulsion systems that go way beyond conventional chemical rockets. The first of these is nuclear thermal propulsion. In these systems, hydrogen gas is heated by a nuclear reactor and expelled at high velocity to generate thrust, offering roughly double the efficiency of chemical rockets. Yet even this falls far short for interstellar distances. A more advanced concept, nuclear fusion engines, aims to replicate the energy production mechanism of stars. Fusion reactions harness the massive energy released when hydrogen isotopes fuse to form helium. If controlled fusion can be applied to spacecraft, ships could potentially reach 5 to 10% of the speed of light. At those speeds, reaching the nearest star system would still take decades, but it becomes something achievable within a single human lifetime. Another fascinating concept is antimatter propulsion. When antimatter comes into contact with normal matter, they annihilate each other, converting entirely into pure energy. Based on Einstein's famous equation, E equals mc squared, this process releases an incredible amount of power. Theoretically, antimatter engines would be the most efficient propulsion system known to physics. Today, however, our ability to produce antimatter is extremely limited, and creating it requires vastly more energy than it yields. For now, antimatter engines remain strictly theoretical. In recent years, laser propulsion systems have also gained significant traction. In this setup, powerful Earth-based lasers push an ultralight sail attached to a tiny probe. Calculations suggest this method could accelerate a craft to 20% of the speed of light. The Breakthrough Starshot project aims to send gram-scale microprobes to Proxima Centauri in just about 20 years using this exact tech. While these probes wouldn't carry humans, they could mark our very first step into interstellar exploration. Yet interstellar travel isn't just a matter of speed. One of the biggest obstacles on long missions is radiation. In interstellar space, galactic cosmic rays carry extreme energy levels that can cause severe damage to human tissue. On top of that, prolonged isolation poses massive psychological challenges. That means interstellar missions will require either ultra-fast propulsion or multi-generational travel concepts. Generation ships are one proposed solution to this dilemma. In this scenario, giant self-sustaining arcs travel through space, while multiple generations live and die aboard. The people who launch the mission won't be the ones who reach the destination. Their children or grandchildren will finish the journey. While technically imaginable, this concept brings massive sociological and ethical questions. Maintaining a stable, closed society for hundreds of years, ensuring resource sustainability, and preserving genetic diversity present huge unknowns. Another approach is cryogenic sleep or suspended animation. Here, astronauts' metabolisms would be slowed to an absolute minimum, keeping them in a prolonged state of stasis. This reduces resource consumption and makes the journey feel drastically shorter for the crew. While this technology isn't remotely ready for human application today, similar biological processes have been observed in certain animals. Even more speculative theories touch on warp drives and wormholes. A warp drive aims to contract space-time in front of a ship while expanding it behind, creating a sort of warp bubble. This would allow the spacecraft to cover vast distances without locally exceeding the speed of light, a concept based on the mathematical solution known as the Alcubierre metric. However, making this work requires conditions like like negative energy density, something that has yet to be experimentally proven. Wormholes, on the other hand, are theoretical tunnels connecting two distant points in space-time. If these structures could ever be stabilized, travel between galaxies could become instantaneous. But as it stands, wormholes exist purely on paper. Another key factor in interstellar travel is the sheer diversity of exoplanetary systems. The thousands of exoplanets discovered so far show us that there could be many environments across the universe capable of supporting life. Rocky planets situated in habitable zones are prime candidates for our distant future. Still, we can't plan crewed missions to these worlds without first analyzing their atmospheric compositions, magnetic fields, and surface conditions in deep detail. So as you can see, no matter how advanced our technology gets, interstellar space will remain a formidable challenge for a long time to come. Of course, as our knowledge and capabilities evolve, we will eventually overcome these hurdles, though unfortunately our generation won't be around to see that day. I hope you enjoyed this video. That's all from me today. Don't forget to subscribe to the channel, like the video, and leave your thoughts in the comments. Until next time, take great care of yourselves, and goodbye.